Number 15. Find all the complex roots. Leave your answer in standard form. Find the complex cubed roots of negative 8i. Alrighty, so we're finding the complex cubed roots of this imaginary number. In order for us to do this, the first thing we want to do is get it in its polar form. So its polar form is going to be r times the cosine of our angle plus I times sine of an angle. We're going to get r and that angle using just that negative 8i. So our imaginary number we usually refer to as z equals to negative 8i, and in general it has a real part and an imaginary part, which we call x and y. So our real part is that number that would be usually in front of the imaginary part. And our y is the number that's in front of our I. So our y is negative 8. Since I don't have a real part, it must be 0. So x is equal to 0. So then we can find our radius using x squared plus y squared equals to r squared. So 0 squared plus negative 8 squared equals to r squared. So 0 plus 64 equals to r squared. So 64 equals to r squared. And then we're going to take the square root of both sides. So I'm going to get r equal to plus or minus 8. Now r is our radius. And radius is a measurement or a length of something. So it's going to be positive. So our r equals to the positive 8. Then we need to find our theta. And we usually either use sine, cosine, or tangent to find our theta. We're going to build whatever function we choose using this x, this y, and this r, and then find the angles that make it true. I prefer cosine personally, so I'm going to go ahead and use that. So the cosine of the angle theta we're looking for will be equal to, well, cosine is my x value divided by my radius. So this is going to be 0 over 8. And then we're going to reduce. So the cosine of theta equals to 0. So then I want to go and find and see, well, what angles makes cosine of theta equal to 0? Well, theta equal to 90 degrees, and theta equal to 270 degrees. But I can only use one of these angles. So I need to figure out which one is the correct one. Well, we can do this by graphing our imaginary number and seeing where it would be logical for our angle to stop. So if I were to kind of doodle an xy plane here, where x is the real part of my imaginary number and y is the imaginary part of my imaginary number, we would plot the point 0, negative 8. Well, the only angle out of these two that gets me down to that 0, negative 8 would be 270 degrees. So that must be the angle that we need. So then our imaginary number z is going to be 8 times the cosine of 270 degrees plus I times the sine of 270 degrees. This isn't actually what we need for this problem. We want to find the cubed roots. So we have to use our complex roots formula. So our complex roots formula is going to be z sub k equal to the nth root of r times the cosine of theta divided by n plus 360 times k divided by n plus I times the sine of the same thing. So of course we know what our r and our theta is. We need to figure out what this k and this n is all about. Well, n is our number of roots. So we're trying to find the nth root, the cubed root. What number do we use for cube? 3. So n is equal to 3. Our k will be multiple numbers. So our k is going to be equal to 0, and then all the numbers up to 3, but not 3. Or up to our n, but not our n. So 0, 1, and 2. So what we need to do is plug in our n, and plug in our theta, and plug in our r, to find out what z sub k really is, and then plug in each one of these k's. So my z sub k is going to be the third root of my radius of 8 times the cosine of 270 degrees divided by 3 plus 360 degrees times k divided by 3 plus I sine of the same thing. And then we can simplify as much as possible before we start plugging in our k's. So z sub k equals to, well, can I find the third root of 8? For sure. It's just 2. That's actually really nice for us. So I'm going to do 2 times the cosine. Well, 270 degrees divided by 3, that's 90 degrees. Plus, well, 360 divided by 3 is 120. So 120k plus I sine of the same thing. So 90 degrees plus 120k degrees. 120 degrees k. So then we can plug in each one of these k's. K equal to 0, k equal to 1, and k equal to 2. And it wants us to leave it in its standard form, which means it wants us to leave it in its polar form. So let's find k z sub 0. So everywhere I have a k in my problem, I'm going to replace that with 0. So I have 2 times the cosine of 90 degrees plus 120 degrees times 0 plus I sine of the same thing. Well, 120 degrees times 0 is just 0. And 90 degrees plus 0 is 90. So it's going to be 2 times the cosine of 90 degrees plus I sine of 90 degrees. And we're going to leave it right there. Then we can find our next one. Z sub 1. So this time I'm going to replace all the k's in my formula with 1. And then we simplify again. So 120 degrees times 1 is 120 degrees. Plus 90 degrees gives me 210 degrees. So this is going to be the cosine of 210 degrees plus I times the sine of 210 degrees. And we want to leave it in that form. So then we can find our last one, z sub 2. And again, we're going to replace all those k's in our z sub k with the number 2. and then we get to simplify. So 120 degrees times 2 is 240 degrees, and 240 plus 90, that's going to give me 330. So the cosine of 330 degrees plus I times the sine of 330 degrees. And it's important we didn't forget that radius on the outside. So this z sub 0, z sub 1, and z sub 2 are our final answers.